Okay, um, thank you for giving us your time this evening, and hopefully what we're going to show you help make sense about how to build an energy efficient home using the 5 passive house principles. I think first of all, I better explain what I'll talk about today, who I am, and what my qualifications are, what is an energy efficient house, building an energy efficient house using the 5 passive house principles. I will explain each of them to you. What are the biggest causes of failures when building a passive house and how we avoid them from happening. There'll be an overview of what I've talked about, and then at the end we'll answer any questions that you have. So first off, uh, who am I and what are my qualifications? I'm trade certified by the International Passive House Institute, a licensed building practitioner, registered master builder. I've been building in Christchurch for over 20 years, and we're not here to sell you any particular product, only look at what works, and we're passionate about building energy efficient homes. So, if you think of your house like this coffee pot, does it take constant energy and money to keep it warm or cool for that matter? And the question is there a better way? Well, we've been keeping things warm or cold for that matter in thermostats for years. So doesn't it make sense to build your house that way? And the question is then, why don't we? This is a question I get asked all the time. What is an energy efficient house? And the answer is, to put it simply as possible, how does the house lose its energy after the sun has gone down? And the less that it loses, the less you have to put back in. It's simple to do, but as you'll see, it's hard to achieve. These are the 5 principles that we use in designing and building energy efficient homes, the 5 passive house principles. And we'll run through them one to 5. So number 1, thermal insulation. What are the benefits of good home insulation? Well, insulating your home to a higher standard will add to your comfort. It'll keep you warm in winter and cool in summer. It creates a healthier home environment for you and your family. It reduces outside noise. It reduces your energy bills. And will have a positive environmental impact. Now, one of the reasons I should say, is the reason we put reduces your energy bills down the list is that, yes, the house will pay for itself over time, but there is a cost that's higher than the standard bill to build an energy efficient home. So it costs you more money in the beginning, but it will pay for itself over time. People who live in these homes will tell you about the comfort, and they'll tell you about the health benefits and how lovely the house is to live in all year round. So the comfort factor and the health are the 2 biggest reasons that we think that people should be looking at living in a home like this. Should this be the answer to poor insulation? Well, unfortunately, this is what many people do. They put a blanket over over them to keep warm downstairs. They go to the cold room in the bedroom. They pull the blanket in over them. They'll have a heated blanket underneath, or they'll have a hot water bottle. And when they breathe out, you can see the CO2 or the condensation in the breath that's coming out because it's so cold in the room. Now, if you Google the World Health Council, they will tell you that sleeping in temperatures below 12 degrees centigrade can seriously damage your respiratory system, and that adults should be sleeping in temperatures of 18 degrees, and babies and older people should be 20 degrees. So it is a problem about how people in the winters and things like that, they get a cold on them. They're going in cold environments all the time. They can't shift the cold because they're in that cold environment where the cold air, the damp air, is being breathed in and causing them problems all the time. So what stops insulation from working? Not being fitted correctly, leaving air gaps. Here you can see an extract fan that's in the ceiling, and round it, the insulation, there's a big gap in the insulation. So there's no insulation round there, and it's just a hole in the ceiling where heat can escape. The other thing that people find interesting is that if the insulation is fitted too tightly, not having enough air trapped between the fibres, then it also doesn't work. The wool insulation works by having the air, as I say, trapped between the fibres. And when it's crushed tightly, the fibres crush together and it conducts the energy across. So it reduces the effect of the insulation. Unfortunately, what happens is that when people are building homes with the home builders and things, is that it's done on a contract. People come in, they fit it as quickly as they can, and this is often the case where it's not fitted correctly, and then your investment isn't working. Moisture is a big problem. The blackness on the insulation here is caused by moisture, and on the white part of the wood you can see fungus growing where the jib has been removed after a few years, and you can see the white fungus on the timber there that's growing, and it causes mold, and then there's all sorts of health issues that can be associated with that type of thing that's going on. Unfortunately, this is how our present building code deals with these problems. So let's have a look at what the cause of moisture is and the damp. So as you can see here, this is the inside of a standard build, the way we do it. So this is your jib line along here. This is your timber frame, your insulation in the walls, and then this is your cladding on the outside. Now, 20 degrees Celsius with 50 degrees relative humidity in the room, 0 degrees with 80% humidity on the outside. Somewhere in this wall has to be 10 degrees. Now, 50% of 20 becomes 100% of 10. So what happened as the air pushes through little gaps, that's around your sockets, around any wires you've got, if you've got any outside taps or you've got anything that's coming through the wall, there'll be air gaps around it, and it carries the moisture through. And as the air carries the moisture, it goes, once it gets to a dew point, it becomes like a mist, and then what it does, it drops the moisture in the wall, and it creates the next thing is that your insulation starts to get damp and wet, it starts to sag, and then you've got no insulation in the wall. You've got big gaps in there. It is a major problem in how we build today. So air tightness, this is the remedy to stop that happening. Let's have a look where a typical house leaks air and creates moisture problems. Here you've got in the ceiling exhaust fans, vented downlights is a big problem, chimneys, round doorways, round windows, any open vents. If you've got a heat pump and it's brought through the wall, you'll have gaps around the pipework that's in there, outside taps. These are all areas where the house will leak, and it'll cause moisture problems over time. One thing that always amazes me, how we build a house and then we pump holes in through the ceiling and we put the downlights in, and then this space here is very hot in the summer, so when we warm downstairs, this overheats and then it pushes hot air into the house, which this heat pump has to cool. In the winter, all the cold air comes in here and the heat pump on again, working over because we've put all holes in the ceiling. So how do we deal with air leakage and moisture problems? We use a moisture barrier on the outside. So the blue paper that you can see here, this building paper, this is 100% waterproof, and it works like a Gore-Tex. So it will not allow any moisture in through the wall. This is your insulation inside the wall here, and all the joints and everything are taped up. Any penetrations, as you can see here with this pipework, are all sealed up so that there's no air gaps round and allowing any moisture to go through. If you put a hose pipe on there, it wouldn't get any water in. You can actually take the paper and use it as a cup, and the water will stay in it. On the inside of the house, we have a different problem. We spoke before about the humidity. Well, the humidity, you can't see it. It's a vapor. And on the vapor here, this is a vapor barrier, this white paper here. Because what the house is doing, as we spoke about before, if it's warm inside and cold outside, it's a high pressure and a low pressure, and heat will always go to cold. So the house is pushing through the walls. It's pushing air through the walls as it breathes. but as it does push the air through, it carries moisture with it. This vapor barrier here stops any vapor going into your insulation, and it keeps it dry 365 days of the year, 24/7. Here's a cross section of how the moisture barrier system works. So again, this is the inside of the house here. So this is your jib board, and then this here is your vapor check Intello on the inside. This is your timber frame, and this is your insulation here. Yeah. This blue one on the outside here, this is your moisture barrier. So it won't allow any moisture through here, and we won't allow any vapor here. So we're keeping this critical part of the insulation dry. This area here is just a service void. Now, in the service void, that's where your electrics and your plumbing go. But you actually get another 1.4, our 1.4 insulation in here, or more insulation in there. In here, in a 90mm wall, you can get up to R2.8. Now, when you consider in Canterbury, the code is R2. Now, most builders will put R2.3, R2.4 in, or even 2.6. But in a wall like this, you can get R4.2 on that wall, which is over twice the code of insulation. And also, the higher the insulation, the better the soundproofing as well with the home. But as I was talking about before, your service is going here, and it doesn't penetrate this vapor barrier where it's going through. Air tightness and testing. So when we're building an energy efficient house, as you can see on the picture here on the left, this is a blower door. Now what we do, this is a fan, and the fan here, we measure the total air volume of the house. And if I tell you, to give you some idea of what I'm talking about, if I tell you that the passive house standard is 0.6 of the total volume of air of the house is allowed to lose per hour. That's what we're looking to get it in a passive house, below 0.6 of the total air volume per hour of what it would lose. Now to do that, this fan here, we pressurize the house up to 50 pascals. 50 pascals is the equivalent of 32, 33 km/h wind blowing against the house. This fan here and this computer measures how much air is coming through there when we've done the calculations. But what we're looking for, we're looking anywhere it can leak. And we're finding in the pressure test, one where it leaks, and also we're guaranteeing the performance of the Intello wrap that we put in. There's two tests that we do. We blow air in and we suck air out with the fan. And the average for a passive house has to be below 0.6 of the total air volume of the house. One thing I always say to people is that if you take a standard house of 200 square meters and it's 2.4 of a ceiling, that's 480 cubic meters of air volume in the house. 0.6 of that is, I think, is 280 cubic meters of air. So with a passive house, it's allowed to lose 280 cubic meters of air per hour. On a standard house, if it's, I mean, some houses we can test and you can get ratings of 6, 7, 8, and the old windy villas will be 25, 30 air changes per hour. So it's huge. People say to me, oh, it's fine in the winter. We just leave the heat pump all the time. It keeps the temperature nice and warm, and we don't have any problems in keeping the room warm. The problem is that the reason you have to keep it on all the time is the amount of energy the house is losing. So if we can take the house to a temperature and we can keep it there by having good insulation and air tightness, it makes so much sense to do that. Here you can see during the blower door test, this is air being blown in, and it goes like a cling film, the paper over the trusses here. And when we pull air out, it pulls and it starts to sag down in the movement of what it is. But this is a blower door test in operation. And what you can see here, these are wires, so these are electrics, and they've all been sealed up, so there's no air leakage around them in what we do, and then all the joins are taped on what it is, so we get a good airtight seal. Number 3, high quality windows and doors and how important they are. So single glazing versus double glazing. Here you can see two houses side by side. And on the left-hand side, you're single glazing. This is with a thermal imaging camera. And you can see the heat loss here in red. Double glazing on the right with the same resolution, you can see here it's much more even than the heat loss here. If you try to sell a house today with single glazing, it's very difficult because people understand the big difference between single glazing and double glazing. Well, this now is what's coming more, because this is old double glazing and this is new triple glazing. Because the biggest area of your house or the weakest part of the house is the windows, either with solar gain or heat loss. So having good windows is vitally important. And also what I'll do, I will cover with you in a few minutes, the importance of the air tightness of the window, because the good quality windows make a huge difference to the pressure test when we do it. How people in the Northern Hemisphere dealt with poor windows. Now, these old sash windows would rattle when the wind blows, and you could feel the drafts coming through. So how they dealt with it, they had big radiators underneath, and they kept their rooms warm by that. But obviously, it's not sustainable, and it's expensive to do so. However, in New Zealand, we had a different method. We were a bit smarter because we used heat pumps to do it. But at the end of the day, poor windows, we're using energy to subsidize the poor quality windows, which really would make more sense to have better windows. So here's a cross section of a typical UPVC triple glazed window. So let's look at some of the things on there. So in the gaps here, this is filled with argon gas. So that's going to help stop the conductivity of the energy across the air gap. The biggest thing though here, toughened low E. So what it has on the surface, it has, in this case on triple glazing, you'll have what they call double low E. So low E is a coating that they put on the glass. Now, when they first did triple glazing, what they did is that with the low E, the center pane here, they coated both sides of it when they first did it. But what that did, that caused the glass to shatter because the low E was so good at keeping the energy or the heat in that it would shatter the glass. So what they do now, you've got 3 panes, so you've got 6 surfaces, like one on the outside, one inside, 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 outside. So they actually coat, there's 2 and 5 on the panes, so that stops that happening. That's how efficient it is. The other thing, how good is low E? Well, one coat of low E, a good coat of low E, is probably as good as the best curtains you can buy on the heat loss or the heat gain of what you get in your windows. The other thing on here you can see is here, these warm edge spaces. So I will probably guarantee if you look at home in your windows, is that here, down here will be silver. And the reason they're silver is because they're aluminium. Now, aluminium conducts energy over 1,000 times more than wood. And your windows or your spaces shouldn't be made of aluminium because it's a great energy conductor. Right? Your saucepans at home are made of aluminium because they're very good at conducting heat. So these spaces here are critical in making the windows perform much better. The other thing I spoke a minute ago about the air tightness. So UPVC windows are the European style windows. They open in, but they also have either side of the window, they have 3 pins, and the handle you can tilt and turn. You can open the window fully. And then as you close the window is pulled back and it's held on 6 points, whereas the standard window is held on 3 points, but one with the handle and 2 of the hinges. When we do a blower door test, the window will literally come away from the seal. So when the wind's blowing against your house, it'll be blowing through the seals, and that's what we want to avoid. Ventilation. This is what makes the house healthy in what it is. So what does poor ventilation do for your health? Do you suffer from any of the following? Asthma, headaches, allergies, eye irritation, fatigue, dry throat, etc. I think maybe 1 or 2 things that surprise you here. So CO2, this is what we're breathing out. So, and what are the safe levels of CO2? Well, CO2 is measured in parts per million, ppm. And the best you would get is 350 parts per million. And you'd have to probably be out at Brighton Beach or wherever with the wind blowing off the sea to try and get anywhere near that. But good air quality, as you can see by the chart, is probably around about, between 500 and 800 parts per million. And it's considered healthy up to 1,000 parts per million, which you would get acceptable in a outdoor environment and whatever. Once you go to 1,500 parts per million, people start to complain about general drowsiness, discomfort, and odors and things. And then once we go past 2,500 parts per million, which you can see here, then it starts to have an increased risk of health damage and with prolonged exposure. And we can have some quite serious problems if we're at 5,000 parts per million or working in that environment. You're not allowed to do that without breathing gear. An example here shows the CO2 levels in a 4x4 bedroom with two parents and a baby sleeping. And what you can see here, this is your time, and this is the CO2 levels here. Now, you can see here, just after 9 o'clock, putting the baby to bed, and the CO2 levels start to rise steadily here with the baby breathing. The door's opened and the CO2 levels drop back down. And then what happens, the two parents go to bed, close the door, and then the CO2 level starts to rise. Here at 2:50 a.m., they open the door briefly to go and get a drink of water, go back to bed. At 5 a.m., open the door wide. One parent's still sleeping, but you can see with the door open wide, the CO2 level starts to drop. And then two parents waking the baby, they come out, open the window, and down it comes. The part about this is that it is rising at 430 parts per million per hour. At 5 a.m. in the morning, we're up at quite dangerous levels of the CO2 level in the room. So it's like trying to sleep at that stage with a paper bag over your head. And as you can see here, how it drops down and people start to feel fresh and refreshed. It's no wonder a lot of people can get up in the morning and feel more tired when they get up than when they first went to bed, because they're actually starved of oxygen if they're in an environment like that. Hydrogen sulfide in a toilet. So this is one of my favorite slides for the humor I think it brings. But this is the stuff that when you go to the toilet, somebody's been in there before you, and you turn around and walk away because of the level of sulfide in there. Now, I took this picture actually at the Passive House conference over in Australia a few years ago. So an extract fan that you'll have in your house actually works. It extracts at 25 litres per second. The one used in the Australian test is 27 litres per second. And a Passive House certified unit is 6 litres per second. So it's substantially less than the 27 litres per second. Here you can see, after 2 minutes, the Australian one on the left and the Passive House one on the right. And you can see here the fresh air starting to be introduced. And this is quite pungent in both rooms at that time. After 16 minutes here, you can still see that it's lingering in the air, or the sulfide is still lingering in the air in the toilet. And the Passive House one here is totally clear. So the question is, how does that work? Well, the reason it works is it's balanced. So for every litre of air we take out of the house, we're putting a litre of air in the house. And it's a little bit like having a glass of water. You can't keep putting water in the glass unless you're emptying it out the other side. And that is what we're trying to do here. The reason there's no air coming out of here is there's no air coming in. So this system, having a balanced system throughout the house, it extracts air out of the wet room. So it takes it out of the laundry, out of your kitchen, out of your bathrooms, and all that steam and energy that is when you're having a shower, rather than being blown out into the street or into the atmosphere, it's being put back through the energy system, and the energy from it, the heating, is actually put back into your home in the winter. The air quality in the house comes through filters. So the filtration or the air quality in the house is better than the air quality outside, and it will deal with things like pollen and carbons of outside, and you'll have it's a nice fresh feeling in the house, and it also is very dry as far as because it deals with all the moisture problems in there, because it extracts from all the wet areas that's going on. Thermal bridging. So thermal bridging is a bridge where from heat goes to cold. And what we'll show you is some examples of design and how thermal bridging, where it's working. So this is a house. It's actually a SIPS panel house. And where you can see here, the purple patches, this is the timber in the walls. The yellow part here is insulation. And here is the 25.8, so it's quite warm in the room. The coldest part is 22.6, that'll be these areas here. And the warmest part is 32.9, which is probably this light here that's going on. So here is a window, and this is a thermally broken aluminium window. Now what you can see here on this purple part over here, the room temperature, it's very warm in here because it's 27.6, so it's quite warm. And this area here is actually 24.7. This area here, down here, because it's in the sunlight, is 39 degrees. So now your thermally broken aluminium windows are radiators. So you've already got a warm house in the summer, but now your windows are radiators and actually warming the house, which again then has to be cooled. Here you can see thermal bridging with heat loss examples. Here, insulated walls here. You can see there's a lot of heat loss around the surface, around the windows. The windows are obviously here very poor for the heat loss. In the corner here, the reason there's heat loss in the corner is when they build houses, they don't put insulation wherever you get internal walls or in the corners. You have to put the insulation in before you put it together or before you put your building wrap on. Here, there's no insulation in the wall, and you can see insulation here. But you can see here areas all the time where the house is losing lots of energy. Heat loss example. If it snows in Christchurch and it hasn't snowed for a few years, and your house looks like this, you've got a problem because you're trying to heat the rest of Christchurch. It starts with the design. So with your house, the correct orientation, we want as much solar gain in the winter, and we don't want any solar gain in the summer. In New Zealand, we only suffer from the cold for 4 months of the year, and one of the causes of overheating were with big west-facing windows, which will overheat the house for 8 months. The sun in the summer will rise here, and it'll be high in the sky. In the winter, it will rise lower and it stays lower. So we want as much, we can shade here, so we can put shading up and we can get as much energy in the house as possible in the winter and keep it out in summer, which will keep it nice and cool compared to the outside temperature. Now, I'd like to tell you that we've come up with all these ideas ourselves, but unfortunately, the elements of passive solar heating is a basic idea and was formulated by Socrates, who designed a concept with 3 elements. And I think he died in something like 450 BC or something. So it was, oops, sorry, I'm getting a bit ahead of myself. Yeah. So again, capturing as much winter sun as possible, keeping out solar radiation in summer, and using a thermal buffer to retain that heat in what he was doing. That's passive energy, passive heating. So we touched at the beginning, what were the biggest causes and failures of building a passive house? Well, number 1 is bad design. So the architect or designer for us has to be passive house trained. Overheating is a big problem with energy efficient or passive homes. And the poor understanding of the critical details by installers or builders. Now, when I go to the Passive House Conference, everyone, they always say, the biggest failure worldwide is the builder or the installer not understanding what the architect has put on the plans and the materials being installed correctly. The failure rate is an astounding 85% worldwide. So it is a major problem. The question for us, how do we stop that? Well, we as a company, we make sure our designers are passive house trained, as I touched on a minute ago. We ensure that sub-trades, electricians, plumbers, etc., all understand the end goal. And we employ and train our own building teams. And we control it from start to finish. That way, we can ensure your investment in what you're doing with us works. And that, honestly, is the only way. However, that is a wrap for us. So I think that now we've got some questions, answer times, if anybody's got some of them. And I think I'm going to have to get Rebecca to come back and yeah, put some questions to me. Here she comes. Right, so start.
Yeah. Hey guys, I'm back again. I don't think that there was any questions that was asked in the chat. It's actually my problem because I'm just saying that we can't actually see the chat from here. Oh no, we can. So if anyone has any questions from anything that they've just watched, guys, if you can pop them in the chat now, and then we can make sure that Robert answers them. That would be awesome. So Curtis has asked, I want to build an energy efficient, but I have a tight budget. What add-ons do I include first? That's a great question, Curtis. I'm going to have to pass you over to Robert. I don't know the answer to that.
Okay, so with tight budgets, there's certain things that obviously you want to do first. And first and foremost is your what gives you the biggest return for your money. Your walls and ceilings are the biggest areas. So having the Pro Climate system that we've shown you with the wraps, that would be your first port of call. Your next upgrade would be your windows. And when I say your windows, depending on cost, your first upgrade with any window is the low E, an argon gas, because even with an aluminium window, the aluminium is quite small in relation to the glass. So upgrading your glass is where you would go to, and then you'd look to, if you could, to upgrade your windows. And as the heat recovery system would be then what you would want to be doing. So if you do them three things, like your ceilings and your walls with your ProClimate, good windows, and your heat recovery system, them are the three major items. The difference between an energy efficient house as well and a passive house is that the passive house is just more of the same. So thicker walls, triple glazing rather than double glazing, and it's just upgrading the basic things of what you would do.
Cool, fantastic. Hopefully that answered your question, Curtis. Just let us know if there is anything else to add on to that in the chat. Great. Okay, thanks, Curtis. That's fantastic. Perfect. Thanks. We'll be in touch. Looking forward to hearing from you. Is there anyone else who has any questions about anything at all that Robert spoke about tonight? Anna has asked, tell us about the heat recovery system.
Okay, all right. So I'll try and explain this as best I can, because the heat recovery system is a session on its own. But basically the heat recovery system extracts air from the wet areas. So from your laundry, your kitchen, your bathrooms, your showers and things like that. And it introduces fresh air into the living areas and to the bedrooms. The air that it's extracting out is that it goes through a system or a box, and the box is like a honeycomb. So you've got two outlets coming in and two outlets going out, and in the middle. So the air that's coming out of the house, which is warm or moist, goes into the box, and the honeycomb is made of ceramics, and so it warms the warm air warms the ceramics in the box. The cold air from outside, as that comes through, is heated by the ceramics and then goes into the house. To give you some idea of the efficiency, if the temperature in the house is 21 degrees, and it's 0 degrees outside, the air that's been introduced to the house through the fresh air system will be around about 17 degrees. So what you're trying to do, you're only trying to raise the temperature of the cold air, the freezing cold air when it comes in the house by 2 or 3 degrees. So it's a great way of retaining the energy in the house. The other thing, running costs, to give you some idea of that, is about $50 a year, because all it is a simple little fan that's blowing air. There's no heating, there's no cooling. It doesn't do any of that. It just replaces the air. And as I say, you've got filters in there. So the filters keep out all the nasties that's in the air. If you suffer from hay fever and things like that in the summer, it's a great relief from, people tell me, it's a great release from the pollen that's in the air.
Cool.
So, yeah.
Fantastic. Thanks. What kind of cost do they start at to install?
Right. Okay. So the unit installed with everything, with the planning and design, you're basically looking at somewhere about $14,000 or $15,000 for a heat recovery. The unit has to be planned. It's not an add-on to a house, so the house has to be designed around the system. So and the way it goes and the pipe work and things like that, how it's done, has to be installed correctly. Yeah, so that's the sort of ballpark figure that you're looking at.
Cool. Hopefully, Anna, that answers your question. Great, thank you. Oh, thank you, Anna, for asking. Awesome. Is there anyone else? Oh, Curtis, can you use heat pumps to heat hot water? Do you use that system?
Yes, you can. And heat pump is the most economical way of heating hot water. I mean, we like a system made by Stiebel Eltron, where the heat pump is actually on the hot water cylinder, and that will reduce your heating cost of your hot water by up to about 70%. So it's a great saving. Price wise, give you some idea of prices. A standard hot water cylinder is around about $1,000, $1,200 for a 330 litre tank. For the equivalent in the Stiebel Eltron system is about another $2,000 that you'll pay, but it will reduce your heating bills, your hot water bills, by about 70% per annum. And the other great thing about it is that it actually goes outside, so it frees up cupboard rooms and things like that in the home.
Perfect, more storage.
Yeah, you got more storage with it. Absolutely.
Right. Awesome. Cool. Cheers. Thanks, Curtis. Awesome. Great question. Is there anyone else who has any other questions about anything we've just mentioned or we've spoken about tonight? Nope.
Okay.
All right. We'll guess not then. Well, everyone here, I believe, is on the email list. So if you do have any questions, please feel free to email whoever you've been chatting to at Energy Efficient Homes, and I'm sure they'll be happy to help. And we'll leave it there then.
Yeah.
Yeah.
Thank you for taking the time to come to this information evening.
Yeah, event online. Awesome, guys. Hope everyone has an awesome night, and we'll be in touch.
Thank you.
Cool. Thanks, guys.
Bye-bye.
Bye.